In previous videos we talked about how binding energy and mass are related by this equation we call the energy mass equivalence, but more specifically we said that to determine the binding energy of any nucleus we have to consider the mass of the nucleus where the nucleons are separate and the mass of the nucleus when the nucleons are bound, and that mass is called the mass difference because there is a difference in mass between those two things. Now if we could determine this mass in atomic mass units, then according to this equation here, one atomic mass unit, which is the fundamental unit of mass when we are using nuclear calculations, is 93.15 mega electron volts. So if we've got a mass difference of one atomic mass unit, this would represent the binding energy. Now, defining binding energy, we said that it's the total energy to either combine or dismantle a nucleus. So either of those will give us the correct calculation. To make it a little more specific to the energy required per nucleon, we used this ratio, binding energy per nucleon. We said that represents the average energy per each proton or neutron. And the other calculation, or the other definition that was important, was this mass per nucleon, which represents the average mass, obviously, per nucleon, or in other words, we can say that the mass of a proton or neutron depends on which nucleus it is found in. Very important conclusion. Then we looked at the binding energy per nucleon graphs, and we said that there were two graphs. The first graph being the binding energy per nucleon graph that looked like this, and the second graph is the mass per nucleon that looked like the green curve there. The conclusion from this graph and these calculations was that a nucleus that like helium or hydrogen that is really close to the beginning of the z equals 1 or 2 part of the graph has the largest mass. So the largest mass would of a nucleon would be found in either a hydrogen, helium, etc. And the smallest mass would be in something like iron here, which has a greater proton number Z. Alternatively, since we have this energy mass equivalence, we say that an element that has a low proton number here has the smallest binding energy per nucleon, whereas an element like iron, which is at the peak of this curve, has the largest binding energy per nucleon. So from this now we will have a look at the relationship between fission and fusion, and we said that any elements to the left of this line will undergo fusion to release a surplus amount of energy, whereas any of the elements beyond this line, which is beyond the iron line, will release surplus energy through fission. So we've covered most of the learning goals in previous videos, but today we're going to focus on defining artificial transmutation, the word transmutation simply meaning to change a nucleus into other nuclei, so the nuclei are transformed, and we're going to compare this to natural transmutation or decay. And finally we'll have a look at fission in the context of a chain reaction, meaning that the reaction can be self-sustainable in that the one of the products released from a fission reaction, a single fission reaction, can then initiate other reactions producing a chain reaction. So artificial transmutation, the word induced is used, which simply means we force the splitting of a nucleus by using a high velocity neutron. Now, since a neutron is neutral, it doesn't experience any of the electrostatic repulsion, so it gets a clean hit at the nucleus. Now, the energy of this neutron is then absorbed by the nucleus, and as a consequence, this causes an elongation in the nucleus, which in fact then weakens the strong nuclear force range, and we know that the strong nuclear force has a very short range. As the nucleus becomes weaker, the repulsion forces kick in, which makes the electromagnetic force win, and we have two separate nuclei which we call daughter nuclei that are produced as part of this reaction. Now, the other thing to notice is that sometimes these nuclei are not divided into two equal parts, so these daughter nuclei would not be the same nucleus. Now, the other thing that's released as part of this transmutation, this induced or artificial transmutation, are these high kinetic energy neutrons. Now, they play a role in the chain reaction, which we'll talk about in a moment. Now, in order to find out how much energy could be released in this type of transmutation, this is one nuclear reaction, or the splitting of one nucleus or one element or one atom. We can find the energy released because we can use the mass equivalence relationship, and that is the sum of the masses released of the released nuclei and neutrons are greater than the nucleus before splitting. Therefore, we have a mass difference. We use that mass difference in our equation here, and we can work out how much surplus energy is released by the reaction. So one of these single reactions or transmutations releases these neutrons we spoke of, and these neutrons in turn may hit other nuclei and cause spontaneous chain reactions. So what happens is the nucleus absorbs the neutron, it divides, producing daughters and other neutrons, and the process continues until all the fuel has been used up. Now, we've just got to be careful when we do our calculations to recognize that one single reaction which has a particular mass, and we can work out the mass of a uranium nucleus simply by considering its molar mass, and it's a term used in chemistry, but we'll work with that term also in physics. Now, if we were to summarize this reaction in the form of a nuclear equation, then we would need to consider a few things. We covered some of this before, and we've also covered some of this in our Year 10 Extension Science course. But what we need to do is ensure that we have a conservation of mass on both sides. That is, the side of the products, if you like, and the side of the reactants. And we simply add up the proton numbers here to make sure that the proton numbers on the left hand side are equal to the proton numbers on the right hand side. We need to do the same with the nucleon number or the atomic mass numbers to make sure that they're equal on both sides, and if they're not equal, we have to balance the equation. And once we've balanced it, then we can start using it to analyze how many atoms there may be in a sample of uranium that maybe we use to produce energy. For example, 1 kilogram of uranium or 1 gram of uranium. We can actually do the calculation and analyze this equation, and we can predict how much energy will be released. So to find the energy released, we said we find the mass defect, which is the mass of the products, minus the mass of the reactants. And by the way, this little sign here means simply an absolute value, so it means your value must be positive, and whatever value you get, you make it positive. Then we use our E equals delta mc squared, our mass defect we know, so then we can apply our atomic mass unit. One atomic mass unit is equivalent to 931 mega electron volts, and from that we can actually work out how much energy may be released by a particular mass in grams or kilograms. One of the learning goals that you'll find in the list of Unit 1.2 was to problem solve or use a nuclear reaction to determine how much energy is released. So here is an example, and we'll start with a fusion reaction. The process is exactly the same. All we need to do is we need to find the mass before and the mass after, find the difference, and then use our atomic mass unit conversion. So delta M, being the mass defect, is equal to the mass of the product, minus the mass of the reactants. Now the product in this case is this deuterium nucleus, so mass of the deuterium nucleus minus the mass, the sum of the masses of the hydrogen nucleus and the neutron. So that's how you would write it in equation form. So when you're solving problems, it's important that you articulate your steps and show you're working in this particular way. Once we found the mass difference, we know that one atomic mass unit is equivalent to 931.5 mega electron volts. We put in the numbers that we're given, and we come up with a value for delta M, our mass defect. We apply our conversion factor, and we can say that a single fusion reaction, that is taking one hydrogen nucleus and bringing the neutron close enough so the strong nuclear force kicks in and binds them to produce 1 hydrogen or 1 deuterium nucleus, will release 2.2 mega electron volts. We use exactly the same process for a fission reaction calculation. In this particular case, this reaction, we write the equation and we balance the equation. Here are the masses of the different parts. We write our delta M, or mass defect relationship, mass of the products minus the mass of the reactants. And in this case, we've got the sum of the products being 3 products, and we've got 2 neutrons here, and obviously the mass of the uranium nucleus and the neutron. Putting in all the values and solving, we get the mass defect is equal to 0.194 atomic mass units, and applying our conversion factor, we have 181 mega electron volts. So what this means is that the fission, the induced fission or induced transmutation of one uranium nucleus or atom or mole produces these 2 daughter nuclei, rubidium and cesium, plus it releases 2 neutrons that have high kinetic energy.